I obviously want to give, say, an overview of what we've been able to do recently in terms of this thing called Goncharov's depth conjecture. It's bracketed in the subtitle, and like the progress and ideas and what we're thinking about there. I won't give anything in terms of like explicit full identities, this is how you will use such and such and such and such, because they get very long and complicated. I want to more give the flavour of how these things work and the theory that goes into, say, predicting them and finding them. And if there's time at the end, I can give some indications of how to prove some things. There might not be time at the end because I promised to stop exactly at 4 o'clock in time for tea. But to start with, I want to recall the definition of multiple polylogs, just to make sure everybody has the same convention to start with, the same as the convention Federico had for the MZVs this morning, so that should be okay. And I'll just always abbreviate multiple polylogarithm MPL, for simplicity. So multiple polylog is this function that depends on some number of indices, we'll call them A1 through to AD, and some number of variables x1 through to xd, and it's this nested sum taken over column n1 less than n2 less than less than nd, x1 to the n1 to the good xd to the nd, over n1 to the a1 to the good nd to the ad with some convergence condition. And I could write something a bit more precise here, but just for simplicity, take all of the xi's to be less than 1 and the series will converge. And you can kind of analytically continue it a bit beyond that as a multi-valued function. I'm not so interested in the numerics of things, so that will suffice. And with the same terminology as in Federico's talk, we have the sort of weight of this thing and the depth of this thing. So the weight is the sum of all of these indices. So weight is A1 plus A2 plus W plus AD. And the depth is just the number of indices. Or depth. It's the convention I'm trying to stick with. And roughly the goal or challenge around multiple polylogs is to understand, or one of the challenges is to understand what the true depth of these functions are. So you can write down some examples of functions that look as if they have a certain depth, but you can show via functional equations and relations they have smaller depth or bigger depth or some different depth.
Surely not bigger.
You can, yeah.
If you have an expression that looks like there's a certain depth, it can't go up, can it?
Wait a moment. In a very silly way, just to illustrate.
Well, maybe if you're deep enough.
You forget. What goes up must come down.
So your goal is to understand what the true depth of a multiple polylog. So in the same way that the multiple zeta values, we expect that the weight is a grading, the same is true here. There shouldn't be any relations between different weights. But you can easily write down relations between different depths. And the stupid example is if you can take an expression that reduces the depth, reading it the other way tells you how to increase the depth. It's a very simple example, but it kind of illustrates the point. So the depth is only a filtration because you can write down examples like E1, 1 of xy plus E1, 1 of yx plus E2 of xy is product of E1 of x, E1 of y. And for the rest of the talk, I kind of want to ignore products because in principle they will be combinations of lower weight things, they will be simpler, so I will just ignore it and say this is 0 mod products. And in particular, we have an example here of how to write Lie2, a depth 1 thing, as a sum of two things of depth 2. It's a contrived example, but it at least shows that the depth sort of, you can have things of different depths being related. The more interesting example, of course, is there's a formula that writes Lie1, 1 of xy, this single term, as a sum of depth 1 things. And I've got it explicitly here, Lie1, 1 of xy is Lie2, y1 minus x over y minus 1 minus Lie2, y over y minus 1 minus Lie2 of xy through as a power series identity on xy less than 1, y less than 1. There's some question?
So how this first one is actually proved?
The first one is actually just an extension of the Stuffle product that Federico talked about earlier this morning. You just write down the two series that correspond to Lie1 of x, Lie1 of y. And one of these is the cone m less than m, m greater than m, and n equal to m. So it's just an extension of things like that. So, let's say the more interesting example is when you can take something of, say, depth 2, a single term, and write it as simpler things, depth 1. The arguments get more complicated, but in terms of depth, it's smaller, it's in principle simpler. And yes, good point. So, actually, I don't know what quite is the history of this, because I would probably attribute that, at least you popularized it in the dialogue paper.
Well, no, I can tell you the history. Sasha once told me that that Li11 can be expressed in terms of dialogues.
Yeah.
And I said, that's impossible. And the proof is, if there were such a formula, it would be so famous and so beautiful, we would have all learned in university. So he showed me the formula, so I lost my bet. I thought, and I still think it's very strange that we never are shown this formula in our mathematics education. He knew it, but he'd known it for years, so I don't know.
But
So
I think even for trilogues, it's like a very old result.
What?
Even for trilogarithms,
it's very, it's at least 50 years old.
Somewhere in like Lewin's book or something.
Oh no, it's much older.
So the trilogue example I will get to in a moment.
Even trilogue.
So at least you popularized it in a sense.
Well, I put it in my paper, so it became well known. And we had a nice bet. Goncharov has the nice property. When you make a bet with him, it's the loser who gets the prize, because after all, he already lost the bet, he should get some compensation. So since I was wrong, we bet for a book, he gave me a very nice book. So I wanted, by losing this bet, I want a book. It doesn't tell you the proof.
Okay, so it has some prehistory before the dialogue paper.
Oh, wait.
In the same way, you can give a formula that gives an expression for Lie1, of x, y, z as a sum of q Lie3s. I will not write that out because it's a bit more complicated, but to give an indication of what it looks like, the argument tends to be things looking like, say, product of 1 minus y, 1 minus x, y, z over 1 minus x times y times 1 minus z. So a bunch of things of that sort of flavour. But if you then try to do the same thing in weight 4 and ask about even the simpler thing, 3.1 or you try to ask about, say, even the simpler object Lie3.1, so a depth 2 function in weight 4, and ask whether you can write Lie3.1 of x comma y in terms of Lie4s. You can try as you might, but it seems not to work. What you can do, however, is write something like Lie1 minus x over y comma y plus Lie3.1 of x over y comma y, this two-term combination as a sum of Lie4s. And I won't give the formula for this, and everything, as I say here, is taken mod products. but it gives some indication that the behaviour changes between weight 2, weight 3 and weight 4. And the question, the goal, the idea is to try to understand how to predict these type of reductions and how to explain why there's the obstruction in weight 4 and predict what, say, the correct thing should be that will reduce. So there is actually a very precise answer to this question, still conjectural in that the Goncharov depth conjecture I alluded to in the title and the subtitle of the talk. But in order to explain how it works, you need to introduce some of the motivic theory and some, like the Hopf algebra and the coalgebra structure. So I don't want to do that in excruciating detail, but sort of just to give the main points. The first thing I need to do is actually write these polylogs as iterated integrals. And the notation is fairly similar to what was in Sato's talk just now. So I'm going to write the A1 AD x1 xd as an iterated integral. Maybe, depending on your convention, there's some sign in front coming from the depth. But it's an iterated integral from 0 up to 1 of differential forms that I'll write as just individual arguments and indicate what they are in a moment. First one is 1 over x1 dot dot xd, followed by some number of zeros, should be a1 minus 1 zeros, so a1 terms in total. Then the next term is 1 over product a2 through to ad, the x2 through to xd, sorry, followed by a2 minus 1 zeros, so again a2 terms in total. And you repeat this all the way down to 1 over xd itself, followed by ad minus 1 zeros. Again, 80 terms in total. So the notation is basically what was in the...
No, can you extend the notation? What is 1 over xd 0 d ad minus 1?
There's a lot of commas missing.
Well, there are commas on that already.
So it's a comma-separated list. 1 over this product, followed by a lot of zeros.
That's not commas, that's a product. The others are...
0, 0, 0, 0, 0, 0.
So this means the zeros are repeated a certain number of times.
Oh, okay.
And so in here, each argument, each thing is corresponding to a differential form dt over t minus, just label one of them as this capital AI, the differential form dt over t minus AI, and use the same iterated integral notation as in Sato's talk. The point now is these iterated integrals, Goncharov upgraded to be framed mixtape motives. So there's some motivic structure that you can then exploit to understand properties and behaviors and functional equations of these objects. So I'll just write lifted the normal iterated integral I to some motivic version denoted IM. And by extension, you can then define a motivic version of the polylog by exactly the same iterated integral representation. And so for the rest of the talk, I will be focusing mainly on the motivic version of the polylog. So in the notation, I might drop the M just for simplicity, but everything at this point beyond to be viewed as motivic. Once you have the motivic multiple polylogs, you have the Hopf algebra structure giving a co-product that lets you decompose this integral into pieces in certain ways and understand the structure. I think at this point I'm obligated to write down what the definition of the co-product is, at least with the semicircular picture that always appears. But actually for the purpose of this talk, I only want to look at things mod products, so I want to look at the Lie coalgebra version anyway. So if we look at modulo products, we get actually a co-bracket. Now, recently I sort of got into the bad habit of just denoting the co-bracket with the same symbol as the co-product would normally get. If I'm working just in the Lie coalgebra, there shouldn't be any confusion, and since one is the image of the other, it's kind of an abuse of notation that I'm going to make now, partly since it's already appearing in papers from Gangl and Rudenko is using the same notation, so just to be consistent. So more copy, I should write a little delta, but let that be. And I can give you the definition of how this acts on the motivic polylog mod products. I would write actually as E with the superscript L to denote that it's the image in the Lie coalgebra. So the formula is the co-bracket of the situated integral is given by summing over I less than j, picking 2 points and cutting out the subsequence it defines as one factor and taking the remaining term as the other factor. So sum over I less than j, xi plus 1, xj minus 1, xj, wedge, because we're in the Lie coalgebra, equal x0, x1 to the xi, jump over to xj, and then continue to xn plus 1. I'm sort of required now to draw this semicircular picture that acts as a mnemonic for how this thing works. So the mnemonic to understand the structure of this is arrange the points of the iterated integral around a semicircle, lower bound on one side, upper bound on the other side, and there are differential forms appear inside. Formula is then telling you to take all possible ways of cutting the semicircle from, say, one point xi to another point xj. And one factor, say this at the top, gives the left-hand bit of the wedge. And the factor down here gives the right-hand bit of the wedge.
Why is this semicircle easier to understand than this very simple formula?
Visual. It's more visual. It gives
That's
maybe
visual. Okay, go on.
If you're trying to compute the co-product of some particular example, you can see, say, where the zeros are arranged, and it's maybe easier to identify. I need to take a cut from here to here, and here to here, and here to here. It's certainly more useful if you're talking about the actual co-product, where you're taking multiple individual segments down here rather than just one, but it's mnemonic in the same flavour.
Where do these motifs live? Are these over a function field?
These irreducibles are periods of mixed state motives over some number field. Excuse me.
I mean, it depends on which whatever it says.
Over Q?
In general,
Over
the
Q
field-
adjoint variables.
Yeah.
So you say that all the x0, x1 are rational.
Not necessarily.
It's a parameter.
I want to do this for. I want to imagine this like as a functional version in a sense. So maybe it's more like well, a period of motive living over some base.
So this formula on the right hand side, you have I, but that should be IL or IM, no? This is all the motive, right? Okay, IL.
Everything here is taking off products. But from this viewpoint, the depth behaves well as with respect to the motivic structure here in the following sense. Like here and then in the top board. So the depth of polylogs in some precise sense is motivic, in that if you write d sub d to be all polylogs of depth less than or equal to d, then you can check that the co-product of something of depth d has a component that is itself of depth d with something of weight 1 plus a direct sum of things of depth less than d wedged depth less than d, the depths sum up to be the original depth.
dd or dd minus 1?
Yeah,
Yeah.
generally dd. The depth stays the same here. Which is why later I will want to ignore this factor completely. So as an example, you can compute the co-product in the sense of dd4 of x looks like log wedge dd3 of x. You have the weight 1 contribution, but you still have the depth 1 contribution. You started with depth 1, you have a depth 1 thing. Whereas the co-product of, say, E31 of x comma y has a bit that looks like log x wedge E21 of xy. Plus a bunch of things of the form E1s wedge E3s. Plus a final term that is more interesting, a E2 of x wedge E2 of y. So you see again, you get the pattern that the depth 2 object gives weight 1 wedge depth 2. Then you get stuff of lower depth wedge lower depth in automatic way summing up to the original depth. Depth 1 and depth 1 giving depth 2, depth 1 and depth 1 giving depth 2. Depth also might go down here.
Maybe one question. In your example, you have a rational function on x and y, but here in your motivic version it disappears.
And then you could specialize the arguments here to be, say, the rational numbers you get in that particular combination, for example.
You can specialize.
In these two cases, the first term is just log x wedge that argument. Is that always the case? So if I have anything is delta, that thing wedge, always log
I don't think
x.
it's not always quite that simple, I don't think. You don't check it. Maybe in fact I've got Lee 3, 1 here, so the weight greater than 1 term here is
Oh,
not
so
letting
it's
you
2.
see the y, but there might be The terms that appear here are really the fact, are sort of very distinctly related to the symbol or the symbol mod products.
Yeah.
So you'd see, simply when computing the symbol of Li1, you'd take the symbol of Li2, compute it somehow, and then concatenate with x. So the structure more generally might have a log x, a log y, or something here that you stick under the symbol. So it's not just as simple as a log appearing there. But in this example, if I look to this side, the keep on now is we see E2 of x wedge E2 of y term here. And this is very much something that you cannot make up by adding any combinations of Li4s. The Li4 term is always purely weight 1, weight 1. And even more so if you always just ignore this factor, the depth d wedge weight 1 piece, it completes out a lot of explaining stuff. You'd see in the reduced version of the co-product that the probability of E4 just goes to 0 essentially, whereas the reduced version of the co-product of E31 is this term. So I write the reduced version of the co-product is ignore the depth d wedge weight 1 piece, and by doing so ignore all of that, all of that, all of that. You get 0 here versus E2 wedge in E2 here.
Sorry, what did you write? Your D?
Why did you
Wait, one.
The first term.
First
Oh,
part.
I see.
Not only the first term, so it's weight 1,
Everything, whatever.
whatever.
Yeah, whatever wedge, weight one.
It's the depth less than.
So not just GD wedge 1, but anything wedge 1.
Anything wedge one.
We can also not only log x, but V1 also, yeah. And it would be ignored. Yeah? So everything in weight 1.
Isn't it just log?
Yeah.
That's what we conjecture.
Could provide it a bit more neatly. If you ignore the depth d wedge weight 1 piece for the reduced co-product, so the reduced co-product of E4 is 0, the reduced co-product of E31 of xy is E2 of x wedge E2 of y minus.
Excuse me, in your definition delta bar, are you ignoring product or not? Or just lower it?
So I'm working purely in the Lie co-algebra, so products are always being ignored.
Okay, okay.
Product appears, it disappears immediately. So, because you see the reduced co-product of the depth 2 thing is non-zero, there is absolutely no way you can make it up by the reduced co-product of the depth 1 things. This is the obstruction that tells you E31 of xy can't be written in terms of Lie4s. But you can have the idea now of, if I take a combination of things, I realize I'm a mistake. Did I write x, y, then that should be x wedge x, y. But The idea now is you could maybe replace or take a combination of several of these things in such a way as this new bit of the cobalt cancels out and get something that is 0, and then stand a chance of being able to reduce it to 4s. And this is really what explains the two-term weight 4 reduction I wrote earlier on. So the idea now is you can even iterate this construction, and instead of using just the co-product to detect when something is depth 1 versus higher depth, you can repeatedly apply the co-product in a certain way and detect when the depth is depth d or depth d minus 1 or depth d minus 2 in a much more fine-grained way. So in order to continue an example in the same spirit, if you look at the reduced co-product of the 4, 1, 1 of x, y, z, you'll see a term that looks like e2 of y wedge e3, 1 of x, y, comma, z, minus another e3, 1 term wedge e2, plus a lot of simpler stuff, so stuff that's the weight 3 wedge, weight 3, and stuff that's of the form E4's wedge, weight 2. So compared to these things, you now see a thing here that we know is generally depth 2. But if you imagine hitting this product again, say always in the first slot. To be more precise, I should define this in terms of the top algebra first and then project down, but we keep track of which is the first slot, which is the second slot. You can iterate again, so you can say always the first slot with the co-product to see when the depth, to see when you generally have a depth 2 term here, and so detect whether your co-product is representing something of depth 3 and so on. So if you say apply the co-product again, always in the first slot here, E2 will vanish, we compute it, that co-product goes to 0. The weight 3 stuff, the reduced co-product will go to 0 because it's always depth 1. Told you the formula for Lie 1, 1, 1 in terms of Lie 3s previously. The Lie 4 here will also go to 0 because it's depth 1. But the thing that survives would be the Lie 3, 1 term wedge Lie 2 here. And you get something like that iterating the co-product gives you E2 of x tensor E2 of E2 of y tensor E2 of z tensor E2 of x, y, z in say the free co-algebra, the third weighted piece of that. Effectively right. Mod triples, mod symmetric permutations of this. The idea now is the second iteration of the co-product has a non-zero piece. So that means it can't come from anything that's purely depth 2, that would have already vanished. It has to be something coming from genuinely a depth 3 object, which gives an explanation why Lie 411, weight 16, is genuinely depth 3. And this feeds into really the formal statement of Goncharov's depth conjecture, which I can give in a precise way here. I'm going to write Bn to be the space of classical polylogs mod products. So this is the depth 1 thing, it's classical n. Then iterating the truncated coproduct k minus 1 times will give you a map from the associated graded piece of the depth filtration. So there's a depth k mod depth k minus 1 polylogs. The conjecture is isomorphic to the free algebra generated by the classical polylogs. The simplified way of putting it is the truncated coproduct. You can use it to get any combination of classical polylogs that you expect, and if it vanishes on some combination of polylogs, that tells you exactly which graded piece it lands in. So the version I will say is a simplified one. Is it a linear combination of multiple polylogs? Has depth, k here to match it, has depth strictly less than k if and only if this k minus 1 fold iteration vanishes. So depth conjecture is this precise statement that lets you see what the depth of a polylog is by what point it disappears under iterations of the coproduct.
Why did he come up with this?
And somehow the motivation for this is maybe going in the direction of giving some conceptual way of explaining why things like this polylog conjecture should be true as one viewpoint. Some way to show or detect why a polylog, some complicated combination, is depth 1 as a key point. And then this is a kind of refined version that you can use to detect all the graded pieces. One implication or application of this conjecture would be in the direction of the key combinatorial step one needs for Zagier's conjecture. Not the zeta one. Which I'll just write very vaguely as saying that the delegate zeta function at value n can be related to classical polylogs of one value. It also has implications or applications in the direction of, say, volumes of hyperbolic manifolds. Because the hyperbolic manifold, the Gangl variant of it, is connected to the coproduct of polylogs. And if the coproduct vanishes, it's telling you, well, if the coproduct vanishes, Goncharov's conjecture will tell you it's depth 1, but the Gangl variant of hyperbolic manifold should be 0. So it's telling you
just before you go on,
Yes, please.
if I just took a general example, can one formulate an analog or Goncharov conjecture? I mean, maybe false, but I mean, I don't see what, is this implicitly dealing with polylogs, or is there something for a general object? What would be the analog of Goncharov's conjecture? Possibly false for a general. You know, what are you doing here? Suddenly I draw a blank. Well, for anything, I mean, just in terms of the algebra. Algebras, yeah. Is that, I mean, can you formulate a statement? Incorrect. But, is there, what is intrinsic in Goncharov's formulation? What are we using from the motivic setup here?
Just 3 points, 0, 1, and
I mean, it's a statement that something is isomorphic to the code, the algebra of something else.
And you need the depth filtration and some properties.
Yeah,
You need the existence of the depth filtration in order to
I mean, you can't do it in general.
But that's not the size of the iteration. So it could be much more general, iterated in, but it's still a depth.
There is meant to be some equality, some duality between, say, the depth filtration defined by some strange presentation of polylogs versus this filtration induced by at what point the co-product vanishes. So you certainly define some filtered piece of that filtration easily enough. It just wouldn't necessarily, you wouldn't have something else to compare it to. So the polylogs, you have a pre-existing this depth that has some other definition.
So it's a property about the depth.
Yeah.
Of the
Depth, which is not
the depth is just the number of iterations.
No, but a formal behavior of the depth.
And you don't know it in advance.
No, I mean, it will be false in general, but just how would you try to formulate?
This defines a certain property of the depth, that the depth of polylogarithm satisfies.
Okay, so it's really a conjecture about the depth.
But it is.
About the associated property. How would you the associated
I'm
property?
confused. There's a statement about this.
Yeah, the delta kind of separates the two.
yeah, the progress.
Okay. So then I'm going to spend the last few minutes talking about what expectations in this conjecture implies and what direction, how far we are in terms of proving certain things about it. So actually, I should probably mention very briefly that in a certain obvious case, when you take more iterations than the weight over 2, so if k is greater than the weight over 2, then there was nothing you can make on the right hand side. It starts with something of weight 2, the B2 part, polylogs of weight 2, and you wanted to form k many of them, and that would already exceed the weight. So when the number of iterations is greater than the weight over 2, well, that tells you should expect that any polylogarithm of weight n can be reduced to depth at most k. And that was actually proven fairly recently by Daniel Rudenko using like a very nice construction of quadrangular polylogarithms that would take far too much time to explain in the last few minutes.
I don't understand the statement. What is k? Just k is anything bigger than weight 2. Instead k.
And just right.
You mean the depth is always less than half the weight? Now I understand that.
That's probably the nicer way of phrasing it. You see, when you iterate so many times, you iterate more than over 2 times, it vanishes. So without setting that up first, I just want to say every polylog is depth less than or equal to weight over 2.
I mean, for just multiple zeta files, that follows from the theorem that the zeta 2223 generate, because they obviously have at most depth. But with known polylogs, no, I'd say just for multiple logarithms, the statement follows from that, but that's quite a hard theorem. Is that known earlier? Is that an easy theorem? No, so it's just the fact. But of course, it follows from that, the 2223 then. Yeah, because the depth of that is
for zetas applied duality, and you go from high depth to low depth. That's probably all you need.
But not for 2, 2, 2, 3, 2, 2. So
but every multiple function of weight k is a combination of 2, 2, 2, 3, 2, 2, 2s and 3s, in which case the depth is obviously at most k over 2, because it's all.
But for multiple zeta values, you should get more than that. Because you never get zeta 2 in the code. I mean, it's should be like weight over 3.
No, if you have lots of 2s and 1, 3, then the depth is k minus 1 over 2.
No, but I think it's because you restrict to 2s and 3s. Also, it's only.
No, but that's a theorem. That's a non-trivial theorem, but it's true. So
I think it's these 2 statements are kind of.
Anyway,
it's a different relative equation for the MCP.
So anyway, the depth conjecture would imply, would certainly imply that depth would be less than weight over 2. This is somehow the unobstructed case, the case where there is nothing on the right-hand side that can cause problems. But you can start looking at, say, some more involved cases. I will write down very briefly. You can make some change of variables to get a function like the. Let me write it like this with a semicolon. In the notation here, the semicolon before the string of arguments means insert that many zeros at the start of the iterated integral. So you can compute on this that iterating the co-product k minus 1 times gives you something of the form u2 of x tensor u2 of xk. So you get something that looks like it should behave purely as e2 in each argument. You can take a combination of things where say you take x, you put something into the first variable that forms an E2 functional equation, some identity amongst these 2's, then this thing would vanish on the co-product level, and Goncharov's conjecture would say this should reduce. So from this formula you get a few very precise predictions, very precise expectations. First one coming from the fact that E2 of 1 is zero mod products. So very clearly zero mod products. I don't care that it's zeta 2. That suggests that this object, when you evaluate it at 1, x included, xk, you should get depth less than k. So k is the number of variables. That means there are k ones there. And something similar if you use the two-term functional equation x plus 1 minus x vanishes under these two. And the final expectation is if you plug in the 5-term relation, stop and move the wheel at 4 o'clock. I'm running slightly over. But at this point, you'll get a few very precise predictions that this depth K polylog should reduce to lower depth. The first one is, you can maybe call it a Nielsen type reduction, because in weight 4, this thing, when you evaluate it at K equals 2,
So what did you write the second term?
down here, putting in 1 minus x and x into the first slot. This type of thing is related to how the Nielsen polylog in weight 4 reduces to classical polylogs, and this will be a generalization of it. Second term, the second type of reduction is this two-term symmetry that tells you how to change x to 1 minus x. We can also do x to 1 over x using the inversion relation. This is being called by Daniel Rudenko a Zagier type formula, because it is an extension of what you gave in weight 4 essentially for I31 of xy plus I31 of 1 minus xy. And the final one is being called by Daniel Rudenko a Gangl type formula because of the 22-term reduction that Herbert gave for weight 4 polylog evaluated on the 5-term relation in terms of mean 4s.
So are these things now proved or predicted?
Predicted. And the thing I want to essentially end with is these are known only for Ks 2 and 3 so far. That is weight 4 and weight 6. There's unfortunately no time really to say how the proof of any of this works, but we are at least making some progress in terms of understanding the consequences and predictions of Goncharov's depth conjecture and being able to deal with it in some cases.
Is this joint work? Who's we?
So we is a sequence of various different people in various different stages. For case 2,
Who hasn't yet done this?
so for case 2 in weight 4, this is essentially a reduction of the Nielsen polylog, so it's going back to something in Lewin or one of Frederick's papers. The two-term relation in weight 4 is, well, one of them was given by Don, the other was given by Herbert, I think. But they're effectively equivalent in some sense. And in weight 4, the 5-term relation was Herbert. And in weight 6, Daniel Rudenko was able to prove this 5-term reduction assuming these two-term symmetries hold. And that was only a couple, 2022, by some kind of involved comment works about how his quadrangular polylog identity degenerates.
Matveiakin.
Yes, it was the Rudenko Matveiakin paper. Apologies. That was done with the assumption of the two-term symmetries holding, and very recently I have proven both of these. So the Nielsen reductions holding in weight 6 feeding into the two-term symmetries holding in weight 6, proven by me, then leading into the proof that Rudenko gave for this 5-term, and altogether you then get essentially the statement of Goncharov's depth conjecture in weight 6, depth 3 is true.